Thank you. So I hope to cover off a bit of the bigger picture of what we're working on in IVM research in our lab. My background is structural biology, which is a bit different to the AI and machine learning I'm going to talk to today. So that's why I have my very esteemed colleague, Stefan Maetschke, to give you a bit of a deeper insight into the algorithms we're developing. So I want to talk about three things today. I want to convince you why we think your eye is an indicator into your health. And I think for those in the audience that are clinicians, it probably doesn't take much convincing. How artificial intelligence can help address eye disease and the burden of eye disease, and give you three concrete examples of where we're developing artificial intelligence algorithms for glaucoma. So the eye is a really amazing organ. This is a picture here. I will use this picture throughout the talk. There's a lot of different things that you can see and measure in the eye, but for the purposes of this talk, I'm mostly going to be talking about structures that we can see in the retina and images of the retina. So in the retina, you can see the optic nerve coming from the brain. This is how you transmit signals from what the photoreceptors in your eye can see into the brain. And you can see coming through the optic nerve, you can see a lot of the nerves coming from the brain and also the vasculature. So there's a lot of things happening there, and it's really important for the diseases I'm going to talk about. So if you can shine a light into the pupil of your eye and then take a picture, this is what you're going to see. This is a picture of the back of the retina, and you can already see these really detailed structures in the back of the eye. So this white disc is the optic disc, and then you can see all of the vasculature in great detail coming out of this optic nerve. And then this spot in the middle of the image here, and this is where you have the highest concentration of photoreceptors. So this is what gives you your sharp vision and enables you to read. So this is a really great image, and you can see a lot of things happening in here. If you look at this image at the top left and you slice it down the middle, you can start to look at the layers of the retina. And this is a very high resolution image of the retina. I'm not going to talk too much about the anatomies here, but there's a lot of different things you can see as disease start to manifest. And so I want to talk to you about how do we train algorithms to recognize this. So these are really detailed bits of data that you can collect. And I think, as technology advances and the way we can image these things very detailed structures advances, we can get so much more information. I'm going to show you a little video here. I hope it plays. This is an adaptive optic system, so you can actually see the vasculature in great detail, real time. And so I'll just play that once more so that you can see it. I think these are some really amazing images you can see. So your eye is how you see. It's one of the ways that most of us interact with the world. It has a really big impact on productivity. One of the things that happens as we age, and we're all aging, is that vision loss can start to occur. And you can see these typical things starting to happen. It can become blurry. That can correlate with what you can see in these images. And not only does it have to do with vision loss, but with diseases that you start to form in your eye. The thing I think that's really important about the eye at the moment and our ability to measure it is that not only can you understand things about how your vision is going, but you can start to understand major important systems. So your neurological system and your cardiovascular system. I think the neurological system is the most important one, because not only can you see pretty much directly into the brain non-invasively, you can also start to get an idea of the health of your brain. And so there's some recent research that supports evidence of the common biomarker for Alzheimer's disease can actually be seen in the early stages of this in the retina. So that's really important as we want to understand more about how our health is going as we age. So this is giving us a picture of how our eye structures look, but how does this correlate with our vision and what we can perceive as happening in day to day? This is images from the National Eye Institute. This is obviously a picture of normal vision. The disease I'm going to talk about today, just to give some context, is going to be glaucoma. And glaucoma is characterized by loss of peripheral vision. And so you can only really see this narrow field of view. And in rare but serious cases, you can go blind altogether. And Stefan, my colleague, is going to talk to you about diabetic retinopathy. And so here you can start to see some real deficits occurring in the vision as a result of the vascular defects that you can have. As I said, vision is one of our important senses. There are other senses, obviously, that are very important, but vision is one of our most important senses. And a recent report said that the cost of the burden of eye disease in Australia is about $16.6 billion with a B. So this is a really large number, and this is what costs you to go to the optometrist, for drugs, clinical trials, things like this. But there are indirect costs associated with this. If you lose your vision, you lose productivity at work. This can have an impact on our mental health and general well-being. So there's a larger indirect cost associated with these diseases. So that's a bit of an introduction about why we think the eye is important. I want to take another step and say, how can artificial intelligence help address these diseases? So as I said, I'm a biologist, and I want to share with you a little bit about what I've learned about artificial intelligence and its capabilities and limitations. So this is a slide. You can broadly categorize AI, artificial intelligence, into three main categories. So there's narrow AI, which is where we are today. Every example that you can see of AI today is an example of narrow AI. And the definition of that is you can train an algorithm for one specific task. And it can do that task really, really well. So it can take in really large amounts of data and then generate some information about one specific task. So for example, self-driving cars are an example, and there are challenges associated with that. They're quite brittle. So this is why you can see these things haven't been adopted in general yet. Spam filtering is another example, and I'm going to show you some examples of narrow AI in medical imaging. But once you can take these algorithms and apply them to it in a broader context, so for example, we all know about IBM Watson winning Jeopardy. You can't take then Watson without a significant amount of retraining and then go tell it to play chess. So this is a really good example. If you can do that, that is when we're starting to move into broad AI, and we have a number of significant advances that need to happen before we've taken this step. General AI is again another probably exponential step into superhuman intelligence. And so this is, I guess, it's really in the realm of science fiction at the moment, which is why I think that the Terminator is not going to come around the corner anytime soon. There are so many steps we need to take in order to get there. But even though the Terminator can generate a lot of anxiety, I think we need to look at these algorithms and understand their capabilities and limitations. And this is why I'm standing here today, because it can really offer a lot to society, and particularly in eye health and disease. So here we are in narrow AI. Before I move on to the example, I just wanted to mention a couple of challenges that we have in terms of applying these technologies to medical imaging, or the medical domain. So I talked about a lot of data. So this could be medical images, it could be medical records, and just to note, any information, this always has to be done in an ethical, secure, private way. And I'm making an assumption here in all of the things I talk about. This is something we take very, very seriously. But even if you have all of that, there is a lack of what we're calling expert-labeled data. So the difference between narrow AI today and the programming systems of the past computer era that we're used to is that program computers are taught. So they have rules, very defined rules, whereas AI systems can learn and adapt to new information, but you have to teach it. And this is where the labeled data comes in. So the medical images are an example, and I will show you how we're developing these algorithms at the moment. But today it really takes, if you have a whole bunch of medical images, that's not enough. You actually have to have expert labeled data, which is the clinicians in the audience might be aware of this. To get the data sets we need to train these algorithms, you need to actually sit there and draw lines around the features that we're interested in. So you need to train it. This is laborious. It's expensive to pay people to do this. It's very boring. It's not actually adding to the clinician overload we're trying to overcome. So lack of expert labeled data. And then even if you have data, it can be messy. So you can have missing information. Maybe the scans had some blurriness. Maybe there was a smudge on the screen. All of these practical day-to-day things compromise the data that we have. Even if you can overcome those barriers, then you are asking about, do you know what the algorithm's telling you? Is it explainable? Can you interpret it? And so this is where I have a lot of conversations with my colleagues in the lab about, okay, what are we actually measuring here? So even given these, we can make some pretty significant steps forward. So today I want to give you now 3 examples of how we're using AI in glaucoma. But before I move on, for those in the audience who don't know about glaucoma, it's a neurodegenerative disease characterised by this loss in peripheral vision. I showed you the slide earlier. And in extreme cases, you lose vision altogether. You lose this vision because you're getting damage in the optic nerve. We don't know what causes this condition, but we do have some characteristics we know that we need to look at in order to diagnose it and then treat it. The algorithms I'm talking about will not do diagnosis. They're all designed to assist clinicians with the burden of all of this extra data. About 300,000 Australians have glaucoma, and about 50% of those are undetected. So in most cases, glaucoma is it progresses relatively slowly. So if you're seeing, you might not notice if you've got changes in your peripheral vision because you can accommodate, like your brain can accommodate these deficits. So a lot of cases go untreated, which is quite serious. So what we need is to detect these earlier, because if you can detect it, then you can treat it and slow progression. And this incidence of glaucoma in Australia is shared globally. And we think that AI has a really important role to play in early detection. As more and more people are aware about the diseases and come and have screening, we can pick these up earlier. We can understand more, we can use it to understand more about the disease. And I'm not going to talk about it too much, but we can also use it in clinical trials and helping getting the right patients into the right trials. So what I'm going to talk to you about in the next 3 examples are different methods we have been training algorithms to help overcome some of the challenges and to make real progress in ensuring that these algorithms can assist clinicians. So the next slide is quite complicated, but we go back to our anatomy diagram. And here again, I'm showing a picture of shining a light into the pupil, and we want to see a picture of the retina from the back. And so this is what we can see. So I mentioned that there are a number of factors that clinicians use to diagnose essentially glaucoma. And so what we wanted to do is take one of those factors and see if we could train an algorithm to recognise this. And this is the optic cup and disc ratio. So each one of these images is from a different patient. This forms what we call our training set. So it might be a little difficult to see, but you can see red circles here in each of these images. And this is expert labeled data. So we have this data and we've said to the algorithm, okay, given all these images and given these labels, the red circles, the darker circles, for those that can't distinguish between the two, please come back and label us and give us the output. And the output is this green circle here, or the lighter circle. But you can see that these overlap pretty well. They overlap better in some images compared to another. But pretty much the algorithm is actually picking up this anatomy that is important in glaucoma. So I mentioned I'm a biologist, and so I'm trying to understand how do we measure the accuracy. I mean, this is a pretty common computer science problem. But pretty much what we need to do now is measure how well this does. So there's this table here, and I talked about our training set, and I talked about lack of training data. So we've taken different increasing numbers of images, trained our algorithm, and then measured how well it did, essentially. And the closer to 1 these numbers are, the better it is. So you can see here we've got an output for 50 images, and then we've got a non-significant, really in the context of what we're asking, improvement. But we've made a huge difference. That's 8 times the number of images we've used to train. So that's 8 times as much clinician time needed. It's actually not that much gain for an increase in performance. So these are the kinds of things that we are trying to think through in terms of how we design our algorithms. This isn't enough to make a diagnosis. This is not about diagnosing. This is about, okay, if you need to look at 1 of these images a day, that's achievable. If you need to look at 200, not so achievable. So optic cup and disc is one way of looking at this. The next one is we can start to look at, I talked about the layers in the retina. So you can actually take a very detailed view of the retina. So here again is our anatomy picture. So here's the retina at the back. We've actually taken a slice and we're looking, this is the inside of the eye and this is the back of the eye, and here are these layers. And you can get this, I don't know, probably a lot of you have gone to your optometrist and you can get these scans done relatively readily. It's called an OCT scan, or optical coherent tomography scan. And essentially what it is getting a really detailed view of the layers of the retina. So this is a normal retina and it looks quite nice. So you can see that the lines are quite smooth, there's demarcations between each of the layers. But in glaucoma, you start to see changes in these layers. For OCT, for one individual patient, you can get more than 100 scans per patient. So it's really important, so it's a huge amount of information. So what we want to do is train algorithms to do this automatically, identify these layers automatically. So here again is this normal picture. Here I've got two different pictures. Thank you to Barbara who's put these slides together. So we've got an image of another OCT image here and another OCT image here. This is clearly, we've changed this, but here you can see some problems in the scan. So we're doing two things here. One is we are teaching an algorithm to pick up the layers, and the second is we're doing a post-processing step to say how well do you think you did. So here's the first image. Here again, this is a false colour image obviously, where we've told the algorithm this is where the layers are. And we've said go away and understand where the layers are and come back with your output. And here is the output. So by eye you can see that these are pretty similar. But then we've taken an extra step and said, well, tell us in the image where you're not certain of where the layers are. And you can see that this corresponds pretty well to these deficits in the image here. This is due to blood vessels in this particular scan. And you can see again here, where we've taken out the details, we can back calculate pretty well. This is really important because if you get rubbish in, you get rubbish out. So we want to understand this. So this is my final slide, and this is my favourite example of one of the algorithms we've developed, the team have developed. What we're looking at here again is an OCT scan. The original scan is the grayscale image. We've overlaid the red. What we're looking at here is a patient with glaucoma, and here is a healthy patient. And this is the optic disc with the optic cup. So what we've done, firstly, ignoring the red parts of the image for the moment, is we've taken a data set of patients and said, all we've told the algorithm is, here is healthy, here is glaucoma. Come back and tell me whether you think a new image coming in is glaucoma or not. And it does it pretty well. It does it better than this. I haven't showed the results here, but there's a citation down the bottom if you want to read the paper. We can actually do better than the current classical standards. But the thing that I think is really cool is then we took again this post-processing step and said, where are you looking in these images? Where are the important features? So here, I mean, it's pretty obvious in a healthy patient, that's where you would want to look. If you look at the patient with glaucoma, this is where you would expect a clinician to look if you're looking for damaged tissue in the optic cup. Same here in the image. This is the most exciting image, I think. So here, this is looking top down. This image is taking a slice through the optic nerve. So again, you would expect to see this light up here. You would expect the algorithm to look there. But in OCT, it was unexpected that it would look in this area. So this area is an anatomy called the lamina criberosa. And this is where the blood vessels and the nerves come through into the optic cup. And it wasn't previously thought you could see enough of the anatomy in an OCT scan, but this shows you can actually get enough information. So not only is this learning from less data, but it's also starting to generate hypotheses that we can then go and test. So I hope in this talk I've convinced you why the eye is an important indicator for your health. You can not only see deficits associated with your vision, but you can also start to understand the neurological systems. And then I've also talked about how AI can help address eye disease, about how it can help address the burden of all the extra data we're now coming in and all the extra people who are coming into the system as our population ages. And then I've given 3 examples of how we're training AI algorithms to help address glaucoma. It's about learning from less data. It's about being able to interpret the results that you're getting, and then it's about being able to start generating hypotheses. And on that note, I will hand over to my esteemed colleague, Stefan, to talk a little bit more about diabetic retinopathy and deep learning. Thank you.
All right, here we go. So in the second part of the talk, I will show you in detail how we can apply AI technologies like neural networks or deep learning to actually diagnose diseases, in this case specifically for diabetic retinopathy. But before I go into the details, I want to clarify a few common terms. Let's start with machine learning. So machine learning commonly describes computer programs that can learn from data. Let's say you take pictures of cloud formations and you train a computer program to predict if it's going to rain or not. And you do this from data. You collect data and you let it learn. Then this is a machine learning problem or a machine learning approach compared to coding the solution using rules, as Natalie mentioned, to do this prediction. So that's machine learning. Artificial neural networks are a specific type of machine learning. There's a very, very large set of different algorithms that can be used. Artificial neural networks are one of them. They are currently one of the more famous ones. And they're called artificial neural networks because in structure and function, they try to resemble biological neural networks. So then there's the term deep learning. If you look at this image, we tend to organize these networks into layers. And the more layers a network has, the more powerful it is, the better prediction it can produce. So deep learning means we have a deep network which hopefully is more powerful than a shallow network. So that's the original meaning. Today, this tends to be a label that's used for next generation machine learning, not always deep networks, just novel algorithms. And then finally, we have artificial intelligence. Natalie mentioned it already, right? So originally that meant really computer programs that strive to simulate or emulate human intelligence to a certain degree. Nowadays, again, this becomes more a generic label related to anything that's machine learning driven. So with that out of the way, let's talk about neurons and neural networks. So this image is a small, tiny tissue cut out of a human brain. And the brown structures, these tree-like objects, these are some of the neurons you can see. So the roots, what looks like roots, these are dendrites where the input signals come in. The round bit, that's the cell body. And then the axon, this trunk, is where the output of the neuron travels along. And we use a very simple mathematical model to describe the function of these neurons. What they're actually doing is a lot more complex, but what we are doing is we're taking input signals. These are these x1 to xn's. And each of these input channels has an associated weight. So these are the w's, wn. And then we just multiply each input signal by the corresponding weight, sum the whole thing up, pass it through the function f, and that generates the output of the neuron. So if you write this one down, the formula is extremely simple. So it's just the weighted sum of the inputs transformed by this activation function f. That gives you the output of the neuron. And the activation function f, the most commonly used one today, it's what's called a rectified linear unit, ReLU. And again, very simple. All inputs that are 0 or smaller than 0, they just disappear. The output is 0. All inputs that are larger than 0, they just get passed through. You've got this linear behavior for the positive values. So once we have neurons, we can start to assemble them into neural networks. And as I mentioned, typically we try to build layers for one reason. One reason is because we found out that also the brain is organized in layers. There's stacks in the brain tissue. In this case, we've got a 3-layer network. On the left side, that's the input layer where the input signals comes in. So these are images, text, all encoded as numbers. Then we have a middle layer, In this case, that's named the hidden layer, and we've got the output layer. So in a standard architecture, a neuron output of one layer is connected to all the inputs in the next layer. I have drawn this here only for one neuron, but imagine all the neurons in all these layers are connected the same way. That's what we call a fully connected layered neural network. If our inputs are images, then it makes sense to organize these neurons not in linear layers, but also in a grid-like fashion. So the image is two-dimensional, so we also build our layers in a two-dimensional fashion. And then the same way you can stack them on top of each other, and you get a 2D multi-layer network. So typically, if you read some research papers, you find these diagrams a lot. It's just a set of boxes. We don't draw the neurons anymore. It's just too many. We don't draw the weights anymore. But this is just a network architecture, a very simple one in this case. So there's one more thing you need to understand, and then you have a complete understanding of neural networks as they're used today in vision, essentially. It's all very, very simple. So this is called a convolutional operation. So on the left side, we have our input image, and the overlaid grid here is trying to symbolize or highlight the pixels in this image. We take this filter, the blue 3x3 grid, and slide it over all the positions in this image. And then we just multiply the underlying pixel value with these weights, the filter coefficients. So in this case, is these numbers -1 to 8. And if you do this, you can extract all kinds of features from images. In this case, this is an edge filter. You can see that the edges in the input image appear as white lines in the output image. And you already guessed it, right? So multiplying signals with weights and summing them up, this is exactly what the neurons are doing. So we can simulate or build this function just by using a 2D organized layer of neurons. The output weights are the filter coefficients, essentially, and the summing up happens in this target neuron at the end. If you look at research papers, then you're going to see these diagrams a lot, right? This is now called a convolutional neural network. You've got the same boxes, and these little blue boxes, they're indicating, okay, this is where these convolutions are happening. Yeah? And that's all it does. So now let's apply it to the eye and diabetic retinopathy. So we have seen this picture many times by now. Let's do it again. So in detail, right? So light enters from the left through the iris, gets focused by the lens, and hits the back of the eye. This is the retina where the photoreceptors are. Yeah? And if you take a camera and you look in the same direction, you put some light on it, you get this image, the retinal image, or what's called a fundus image. Looks like this. It's just beautiful. The dark spot, right, that's the fovea, highest resolution of photoreceptors, best vision in that area. And then at the bottom, I turned this a little bit around so it matches better up with the diagram. That is the cup and disc, so where the optic nerve and the blood vessels entering the back of the eye. And that's your blind spot, so you can't see anything there. So what we want to do is we want to essentially diagnose or detect diabetic retinopathy. What is it? So diabetic obviously comes from diabetes. People that are suffering from diabetes are affected by this disease, and retinopathy means just damage to the retina. And it's caused by leaking vessels in the retina. And if untreated, in the long run, it will or can lead to blindness. The symptoms, Natalie showed you a picture. So you typically blind or dark spots in vision, blurred vision, and in the end stage, then complete loss of vision. And treatment is typically eye injections or laser treatment. None of that is pleasant, and none of them really reverses glaucoma, diabetic retinopathy. It's slowing down progression, maybe stops it, but no reversal. So early detection is important. The earlier you can treat it, the earlier you can slow it down, the earlier you can stop it. So now this is a fundus image of a person suffering from severe DR, severe diabetic retinopathy. And there's two major pathologies here. So these red dark spots, that is blood vessels leaking blood into the retina. And obviously the blood is obstructing the photoreceptors and that's obstructing your vision. And these yellow spots at the top, these are so-called exudates. And that's lipids leaking the vessel in the retina with the same effect, obstructing photoreceptors, in the end obstructing vision. So diabetic retinopathy is classified or assessed in so-called severity levels, starting from mild over moderate, severe to the worst level here. And what we want to do is we want to use a convolutional neural network and predict these severity levels given a fundus image. So this is work in our lab that describes in detail how we do this. I'll give you only a summary. We take a fundus image, we have seen this before, we pass it into a convolutional neural network. In our case, that network has 25 layers and several million weights, so it's a decent sized neural network. And we also give it, and Natalie mentioned that, for training purposes, the corresponding DR severity. So each image has to be labeled with the ground truth, with the severity we want to be able to recognize in the long run. And then we start to train. So we cycle through these images many times. And at each cycle, we adjust the weights, these filter coefficients of these convolutional operations, a tiny bit to make the network a tiny little better. So that's an automated algorithm. We don't do this manually. This is a computer learning algorithm that does that. That usually takes many hours. In our case, it takes about a week. And we have around 35,000 images. So it's a decent data set. Once you're done, you obviously want to know how well do we do? How accurate is this predictor? And one of the matrices used to assess this quality is the so-called Quadratic Kappa score. This is essentially measuring the agreement of these labels between what the predictor spits out and what you know is to be the ground truth. Yeah? A Kappa score of 1 means perfect agreement. A Kappa score of 0 means complete disagreement. We achieve a Kappa score of 0.85, which is roughly similar to what human graders achieve on that same task. So that sounds fantastic, right? So very simple. You grab some data, you put it in the machine, you train for a week, and you're done. So a computer can do a task which is fairly challenging for a human being and can do as well as they do. But there are a few issues. So we're going to talk about this next. So what are the drawbacks of this one? And I have to say up front, this is not specific to our system. That's not specific to DR severity assessment. This is a general problem of convolutional neural network architectures. Yeah? They're all suffering from these issues. So this is not our work. But what these researchers did, they looked how sensitive a neural network is towards small changes in the input image. In this case, these systems were trained to recognize objects in images. Yeah? So we have a soup of bowl here, and actually the image contains the soup of bowl. It also contains the thumb, it contains a spoon, and so on, but the soup of bowl was recognized correctly. And then we make this image a little bit brighter, and it becomes ice cream, which is obviously wrong. I've got 2 more examples. So here we have a police van classified by the system as a moving van. Not entirely right, but not completely wrong. If we shift this image a tiny bit to the left, you probably won't see it now, it becomes a space shuttle, which is entirely wrong. Yeah? And the last one, so, oops, you can see it already, yeah, tandem bicycle, and the whole image is just squeezed a tiny bit. You won't be able to see that, and it becomes a horse cart. So to summarize this section here, so small changes to the input images, which are invisible or completely irrelevant to humans, can cause catastrophic misclassifications. Yeah? Movie van to space shuttle, this is not acceptable. So CNNs, these convolutional networks, are brittle in unforeseeable ways for humans. If you have a system that achieves superhuman performance in recognizing objects, you would also expect it to make human-like errors, and they don't. Yeah? This makes this one very hard for humans to trust in these systems, and in the medical domain, this obviously is an issue. So far we have talked about honest mistakes of these systems. What about malicious, purposeful attempts to fool such a system? Yeah? They are so-called adversarial attacks. So in this case, again, system was trained to recognize objects and images. Here we have an image of a sports car, and the system correctly recognized, yes, this image contains a sports car. Now what you can do is you can add a specifically designed noise pattern. Yeah? This one is enhanced, so in reality it's a lot weaker, you won't see it, and you just add it to the image. And if you do this and you give it to the classifier, your fancy sports car becomes a toaster. So if you look very carefully, you can see this overlaid noise pattern, but it's very hard to see. So this is one problem. You could argue, well, if it's a self-driving car application or a medical system, this would require that you actually have access to the classification system. You need to be able to input images and monitor responses to design these noise patterns. And usually you wouldn't be able to do that if you don't have access to the system. Unfortunately, you can do this in the physical world as well. Again, this is not work from our lab. So here we have a system trained to recognize traffic signs. And we have a stop sign here, there's graffiti oversprayed, there's 2 stickers on it, but the system has no problem in recognizing this is a stop sign. So what these researchers did, they put stickers on it, again, specifically designed, and now this sign gets classified or recognized as a speed limit 45. Yeah? Obviously, you don't want to have this one in a self-driving car. And this is already my last slide, just to summarize. So now you understand convolutional neural networks. Is the main AI technology used nowadays in the vast majority of vision tasks. These ones are just stacked texture filters, nothing else, and they're very simple fundamentally. So they're trained from many example data. So we need huge data sets that are labeled, and Natalie mentioned that. That's a bit of an issue. The good news is, for many vision tasks, they can reach superhuman performance. They're very good in detecting textures. So ImageNet has 100 dog breeds, and they are outperforming every human on dog breeds because the texture of the fur, they do very well. If you're talking about thin objects, transparent objects, they're doing badly. No texture, difficulties in recognition. They have been successfully applied for medical image diagnosis, but largely in the lab because there are issues we have to deal with. So these need to be solved first before we uptake this one in the real world. So I mentioned that they make stupid mistakes, right? Space shuttle and car. Beyond that, they have obviously no common sense. If I take a picture of a pancake and pass it on to our DR severity classifier, it very happily and confidently says, okay, this person has DR, severe DR. Yeah, there's no common sense in filtering out these images. You need to take extra steps to filter these ones out up front. And there's also no reasoning, right? So if you have a system that detects objects and says, well, I found a car, it can't tell you, well, I saw a wheel, a mirror, a windshield, the shape of a car. I think that's why this one is a car. Or it's round and blue, it's a blueberry. They don't tell you that. You only have a huge amount of weights, and it's very hard to understand why they classify what they're classifying. Yeah? There's no reasoning happening on that side. A last word, I mean, all these are active areas of research, and we're getting closer to solve that, but currently, this is still things we have to deal with. And that's it from my side. Thank you very much for your interest.
Of course, I want to thank our partners. This event would not happen without their very generous support. And please, again, let's thank our speakers, Natalie Gunn and Stefan Maetschke. Thank you.